If you've ever imagined being famous, and if your idea of fame includes wealth and acclaim, perhaps fundamental physics isn't exactly what you're looking for. More than 2,000 years ago, the Greek philosopher Democritus brought us a revolutionary idea by suggesting that everything around us, rather than being made up of earth, air, fire, and water, consists of tiny indivisible particles called atoms. He believed that these atoms were the real building blocks of matter. Fast forward to 1783, when the English clergyman John Michell pondered something extraordinary. Analyzing Newton's laws, he theorized the existence of objects so dense that not even light could escape them. Just imagine, stars that are visible not by the light they emit, but by the light they capture. Michell called them dark stars, and yes, you got that right. He was talking about black holes long before they became a popular concept in science. Back in the early 1920s, Theodore Kaluza put forward an idea that even Einstein considered extra dimensions. What does this really mean? Where are these dimensions? How do they work? And how could we detect them? You'd be amazed to know the influence gravity has on our lives every day. Just imagine, Albert Einstein, just over a century ago, was obsessed with transforming our understanding of this familiar force into something completely new. After 10 years of uninterrupted effort, since the unveiling of his special theory of relativity in 1905, Einstein found a revolutionary way to explain gravity in 1915, the general theory of relativity. But wait a minute, turning gravity into geometry? Yes, that's right. According to Einstein, gravity is actually the curvature of something called space-time, which is a kind of geometry in 4 dimensions. It's something that's all around us, but it's invisible, like Wi-Fi. Entering the scene is Theodore Kaluza, a physicist with a background as curious as the mystery series we love to watch. Born in Prussia, which no longer exists in the way it used to, Kaluza came up with an idea that sounds like something out of a science fiction movie. What if, in addition to the 3 dimensions of space and 1 of time that we already know, there was a 5th dimension? Kaluza showed that by throwing this 5th dimension into the mix, Einstein's equations not only made sense, but also opened the door to totally new things. These equations were transformed and revealed a new force that could go hand in hand with the electromagnetic force, which is already well known to us. Published in the Proceedings of the Prussian Academy of Sciences, with the support of Einstein himself, this result not only expanded the theory of relativity, but also introduced the idea of additional forces in the universe. However, despite the depth and beauty of this discovery, it went unnoticed for decades. After all, the world was plunged into an era of turmoil, with the rise of National Socialism and its nefarious ideologies. During the hectic 60s and 70s, when even music had a new vibe, science wasn't left behind either. An Italian physicist called Gabriele Veneziano had a brilliant idea: string theory. Imagine it as a new recipe for understanding the super powerful glue that holds the center of atoms together, known as the strong force. In the beginning, it wasn't all flowers, and the theory faced a few stumbling blocks. But you know, scientists are curious by nature. They continued to be fascinated by string theory, wondering if it might be the key to unlocking the mysteries of gravity and perhaps even explaining everything in the universe, in a super theory of everything. After a few years, in a eureka moment in the rainy town of Aspen in 1984, Green and Schwartz discovered a solution to a calculation problem where the probabilities simply didn't add up. The world of extra dimensions, until then a marginalized topic, exploded into an intellectual gold rush. Currently, what we know is that we usually follow the 3 known dimensions, but have you ever wondered what would happen if there were 4, 5, or even 9 spatial dimensions? Just imagine, we're used to moving up and down, forwards and backwards, sideways. But what if there were more? The idea of additional dimensions may not be intuitive, but let's try to visualize it together. Think of a long, thin vine. To an ant walking along it, that vine represents practically a single dimension, front and back. What if, for us, the extra dimensions were so small that, with all our technology, they were still essentially inaccessible? It would be like trying to assemble a Lego model using boxing gloves. These mysterious dimensions are not just mathematical speculations. They influence the type and number of elementary particles we can observe. The particles that emerge from these extra dimensions, called modules, are like the echo of a larger, invisible, but infinitely influential reality. Now let's talk about something exciting: the Large Hadron Collider. Why not use this powerful machine to smash particles with enough energy to reveal these modules? Well, here's the kicker. Gravity, that force that keeps our feet on the ground, is absurdly weak compared to other forces in the universe. This means that, even in the most powerful colliders, producing particles that interact mainly through gravity is a colossal challenge. It may be that these particles, if they exist, are so elusive that we will never be able to detect them directly. But here's the irony. If we do manage to create these modules, they would probably have an incredibly long lifespan due to their weak interactions. This contrasts dramatically with particles that interact strongly and decay almost instantaneously. The beginning of the universe, marked by a violent expansion known as inflation, may have been the only time in history with enough energy to create these exotic particles. At that time, the universe grew exponentially in fractions of a second, and maybe, just maybe, during that brief period, the modulus particles were forged in the furnaces of cosmic creation. But like a bell going silent, the particles eventually decay. Their masses don't disappear. They transform into new forms of energy, like the photons that are the particles of light. As the universe expands, the energy of these light waves decreases due to the Doppler effect. The same phenomenon that makes an ambulance sound sharper when it approaches and more serious when it moves away. The modules, however, are different. Their energy is not linked to movement, but to the very existence of the particle. As the universe expands around them, these heavy particles keep their energy intact, without being dissipated by the Doppler effect. But here comes the big question. If the models really exist, could we detect them? After their eventual decay, they could have produced a cosmic background of light and almost untouchable particles, called axions, which could still be buzzing around the universe. Detecting these axions would be a monumental challenge, but not impossible. Using powerful magnetic fields and advanced telescopes, one day we could capture these cosmic fugitives, proving the existence of a universe much stranger and more wonderful than we ever imagined. Well, folks, that's it for today. We've come to the end of another video. Comment if you liked it, subscribe to our channel, and make suggestions for new topics.